Hello everyone, welcome to our course project of linear algebra. We are group 24 and we would be talking about eigenvalues and dynamic stability analysis. Now, uh, before we further talk about dynamic stability analysis of system, let's talk about what do we mean by stability. Now, stability could have different meaning with respect to the type of system we are analyzing. For example, if we are analyzing electrical systems, their stability could be Bibo stability. By Bibo stability, we mean bounded input, bounded output. That is, if we are feeding the system with some bounded input, we are expecting some bounded output. Now, with respect to systems such as aircraft, then their stability is further classified into static stability and dynamic stability. Now, what is that? Firstly, we'll talk about static stability. That is, suppose an airplane is flying and sudden gush of winds come, which we say perturbation. And suppose that gush of wind tend to rotate the airplane upwards, which we say pitching movement. Now, due to that perturbation, what is the instantaneous uh, reaction of the airplane? Is it able to come back to its original position instantaneously? If that is so, then we will say that the airplane is statically stable. Now, another stability is dynamic stability. That means with passage of time, ideally we say as time tends to infinity. That means with long time duration, is the airplane able to maintain its stability or the current state and able to overcome the various kind of perturbations? If that is so, then we say that the airplane is dynamically stable. So this is how we analyze stability with respect to aircrafts: dynamic stability and static stability. Now, um the linear algebra approach, mainly the eigenvalue concepts, could be used to find out whether an airplane would be stable, or if we talk about electrical system, whether an electrical system would be able to give bounded output with respect to bounded input or not. For aircraft, whether the aircraft will be flying in a stable manner or not. That could be find out just if we are able to find out the eigenvalues of uh, the equations that we get from various kind of parameters. We will discuss what we are exactly talking about within a few minutes. And before that, let's talk about in terms of mathematics what we mean by eigenvalues, how we find it out. Now, suppose we have a vector x and we multiply with some real value lambda, then x and lambda x are collinear. The determinant operation of this operation is 0. So we do a minus lambda I into x, that is equals to 0. Now from this we find out the what is the determinant of a minus lambda I, and we get the roots, and those roots we say that they are the eigenvalues. Now, just to illustrate one example, we have written here that suppose we have a matrix A which contains 2 5 4 5 and 2 2 minus 3. Then we arrange that as a minus lambda I put equals to 0 and find out the determinants. And as we try to find out the determinant, we get an equation which is a characteristic equation, and we solve the characteristic equation to find its root, and roots of this characteristic equation are the eigenvalues. Now, what is the physical significance of eigenvalues? In terms of control system stability analysis, those eigenvalues are basically the closed loop poles, as we say, and the position of the closed loop poles are very crucial in determining the stability of a system, whether a system is going to be stable or not. Now, um, we can talk about second order system, we can talk about a third order system, we can talk uh, in order system, and how we solve an in order system are as follows. So we would be talking about the state space approach of solving equations. So initially, suppose if we talk about mm electrical systems, then we will then the storage elements that are there, that is capacitors and inductors, we will find out the voltage and current equations. And for systems such as the airplanes, we find out the force and moment equations. And by solving those physical variables, we get a differential equation, say for example a second order differential equation, or maybe say in nth order differential equation. The approach of state space is to convert that nth order differential equation into a first order equation having n variables. We just replace those orders, that means nth order, that means we have a nth order differential equation, we just replace each order with a new variable, and how many variables we'll add, that is equals to the order. That means if it's an nth order equation that we are getting by solving those physical variables, then we'll take n state variables, and we will try to have a generalized form of those equations as, say, x dot is equals to ax plus bu. Okay, so till now what we have done, we have a system which may be electrical or mechanical or maybe aerodynamic systems. From them we will obtain the equations from the physical variables. For electrical systems it could be voltage and current. For aircraft systems it could be force and moment equations. So ultimately we have a time domain equation, which is a time domain equation which is maybe nth order. Now replace those in order into nth order system into a first order system having n variables, so that it looks something like x dot is equals to ax plus bu and y equals to cx plus du. And these, once we do that, these matrices A, which is called a system matrix, that that would be very crucial in determining various parameters of that particular system. So just imagine that just by from the equations and getting a matrix A, we would be able to guess on various kind of physical features of that particular system. So that's what we'll do. Now once we get the matrix A, which we call a system matrix, we will try to determine the eigenvalues from them. Just as we have seen previously, that once we have a matrix A, we will find out the eigenvalues and check out are the eigenvalues positive or negative, or what are they, because those eigenvalues are nothing but the closed loop poles. Now, as those are closed loop poles, um, those we can have a good idea about the stability of the system. If it happens that the real part of lambda, that means the eigenvalues are negative, real part of the eigenvalues are negative, that would just mean that the poles are left-sided poles. And if it is also having imaginary part and real part less than zero, then that would have this kind of profile, that is exponentially decaying profile, and it will be dynamically stable system. Now, if it happens that the eigenvalues that we find, it has real parts greater than zero, that would mean that oscillations would keep on growing as time tends to infinity. That means it will be a dynamically unstable system. It will not be a stable system. Okay. Now, if it happens that all real parts of the eigenvalues are less than equals to zero, and some real parts of eigenvalue, I mean, some eigenvalues are zero and some eigenvalues are having a real part as negative. Okay, then that will be a neutrally stable system. That is the meaning of that eigenvalue. So once we find out the eigenvalues, we can talk about many kind of physical parameters. Say for example, we can talk about the controllability of the system, we can talk about the observability of the system, and then we can obviously we can find out the what are the frequency, what are the natural frequency of that system, what is going to be the what is the the damping ratio of the system. All these parameters could be find out just we obtain the system matrix A and try to solve that with the approach of finding the eigenvalues. So therefore, we can conclude that eigenvalues of the system matrix reveals the characteristics of the system. Now, based on the signs of eigenvalues, transient response of the system either increases or decreases as time tends to infinity, and stability of the system can be ascertained based on system eigenvalues and its sign. So that's all from our side. Thank you.